of the semester. Okay, so let's get started. Apologize about the technical difficulties today. This whole upgrading this room has been a disaster. Definitely does not feel like an upgrade yet. Well, maybe the computers, but even those have some issues. Okay, good. All right. So I am recording this. Let's see how much room I've got for recording. Okay, I got plenty of room. All right, so I'm going to open this up as a PowerPoint and go through it, and then just like we usually do, I'll do some demos. All right, so today we're going to talk about hydrologic surface modeling. This is one of the terrain modeling parameters that we talked about last week. Specifically, we're going to get into this upsloped area, flow length, upslope length, profile. Well, we talked about that a little bit. So these are what we're going to talk about today. And we're going to look specifically at some applications of doing this type of modeling and how you'd actually implement it. Because once you perform the basic steps, the question still is, well, what can I do with this? So we're going to answer both of those questions. Well, first, we need to talk about what you're doing. And that is that we're doing hydrologic modeling in GIS. So a digital elevation model, it gives us information about the shape and characteristics of the Earth's surface. It's useful for lots of things. But one of the things that it's pretty useful for is understanding how water flows off of the Earth. Now, the shape of the Earth is not the only characteristic that determines how water flows off the Earth. What can you think of other things that might? Yeah, differences in soil, including even if there isn't soil, like if the top surface is paved. What do you think that does to water? Yeah, I mean, it makes it so there's more runoff. It doesn't always speed it up if it's like a big paved bath and it kind of fills up. But yeah, typically, given a constant slope, it will speed it up to have less permeability than more permeability. So what happens when residential development occurs? Well, you can model that. We could say, okay, well, right now this stream handles X cubic feet per second of water. What happens if we put a residential development in? How much more water are we going to get coming through this area? So how does this affect the watershed? And how can we mitigate these things? So one of the advantages to GIS system is that we could set up a model to help us understand this process and how it would affect the volume of water and the time that water was going to reach a certain point. And then we could modify parameters slightly and say, well, what if we built a retention pond that would grab this much water? Or what if we made sure that we only put this much impervious surface in this new area? How could we how would that change the flow? So these funnel into these things that are sometimes referred to as best management practices and help us to manage development or changes to the environment by building a model. So hydrologic modeling involves using elevation data, but commonly there are other inputs. Got soils, water table, things like that. So we're going to look at how water flows off the surface of the Earth. This is like an older representation of a USGS USGS quad that's draped over a digital elevation model. So that's how that was created. You could do that in in ArcGIS Pro nowadays. If you want to, you can create 3D data right there. 2 years ago, when you run ArcMap, you had to run ArcScene to create something like that. Okay. So back when I took a class, mapping class as an undergraduate, we actually had an exercise where we had to do this. I don't know if you've done this, but we had to delineate what we call a watershed on a paper map. Okay? When you delineate a watershed on a paper map, a watershed, does anybody know what a watershed is? Yeah. That's pretty close. Yep. All the area that supplies it can be actually any point. So it's defined by a point location. It's the upstream area of any point. So all your wording works too. All the area that supplies that point. So if I was to go out here in the middle of the quad and stand in a particular location, the upstream area might be pretty small, okay? Especially if I was on one of those rises. Okay. But yeah, that's the basic definition of a watershed. It could be really large. If I went down to Venice and stood on the banks of the Mississippi down there, I don't mean Venice, Italy, down there in the end, then what's the watershed? What's the area that's upstream of Venice? Yeah, it's like, like what, over a third of the United States, pretty much. From Montana all the way over even into Illinois some of Illinois is, actually a good chunk of Illinois. And actually, even further, because Ohio goes into the Mississippi. So, yeah, it's a huge, huge area. All right, so watersheds can be big or small, but technically a watershed is an area defined by an outlet point. And so you can define a watershed on a topographic map like this by following the edges perpendicular to the contour lines. So perpendicular to the contour lines causes us to stay in the same watershed until we reach a ridge line, and then staying perpendicular to the ridge lines and following that all the way around. So I drew this boundary here, just roughly. It's probably not precise, but it is the way that we used to define watersheds when we used to want to study watersheds. And then even if we were using a GIS system, when I was an undergrad, we'd then stick this on a digitizer tablet and actually draw the line in. Okay. So those are the good old days. The reason why I'm showing you that is to drive home a little bit more about what this is. Okay, we know that water that's over here would flow out over in this direction, just because we can see it on the contours. Water in this area is obviously going to flow down the hill here. So I'm going to define a few more terms here, besides just watershed and outlet point. ArcGIS and actually several other GIS software packages actually call that outlet point a pour point. So a pour point is a location at which the contributing area can be determined. It's actually the only other input that you need besides the elevation data in order to derive a watershed. Okay. All right, now there are other products that can be derived through hydrologic modeling in GIS. The first one here, it says drainage system. Drainage system is the system of it starts off with just flow direction. In other words, where water flows and what direction it flows. Eventually, if there's enough upstream area, what's going to happen? If there's enough water flow, as you get downstream, if I go out in the quad, it's land. But eventually, if you get enough water flow, it's not land anymore, it's a stream, a creek, a river. Okay? So the drainage system is all of that network that gets created as it travels to its outlet. So it's direction water is flowing in every single cell. All right, as well as the amount of accumulated area for every single cell. So those can be derived using GIS. The drainage basin is just another word that's more general, I think, than watersheds. I don't know if it's more general or less general. It's a synonym for watershed. Some other synonyms for watershed include basins, catchments, or contributing area. However, sometimes catchments, particularly of those words, gets used to mean something that's not necessarily a watershed. It can be a part of a watershed, which gets us to the next term there. Subbasin is used a lot, but sometimes you'll hear catchments replaced for subbasin. So subbasin is an upstream area flowing into an outlet as overland flow. And then pour point we already defined. A drainage divide is basically the edge between two watersheds. And you've probably heard the Continental Divide, right? I drive over the Continental Divide every year when I travel back to see my sister or my mom or my dad. The Raber family besides me all lives out in California. So somewhere in New Mexico, I travel over the Continental Divide, which is the boundary between the water that flows into the Pacific Ocean versus the water that flows into the Atlantic. Sometimes, occasionally, you're just driving around and you actually see a sign that says, entering the Pearl River watershed or the Mississippi watershed. All right, so this is a GIS-based raster modeling class. And so we're talking about digital elevation data sets. So we're going to talk about how this is modeled in GIS. So we have our elevation data. Our elevation data, of course, represents elevation values at regularly spaced intervals on the surface of the Earth. We talked about that a lot last week. Here's an elevation data set draped on a shaded relief model. It's pretty easy to tell where the water would flow. Okay. Notice that this particular watershed has a flat upper end with a few tributaries, and then those eventually lead to more relief. So that's a characteristic of this watershed that's different than the characteristics of some waters. Some watersheds, like in North Carolina, especially eastern North Carolina, western North Carolina, start off really high relief, and then they come on to lower flatlands. The opposite happens. And that actually changes the effect of the water flow. So if you had a storm in this area, there would be a delay, a greater delay before the water got, like, let's say halfway through this watershed, whereas in the watershed I just described, it would come down very quickly because of the increased slope, and there wouldn't be as much of a delay. So hydrologists that study this sort of thing would actually refer to that graph where we would map water flow as a function of time as a hydrograph. So hydrograph, I should have a slide that shows a hydrograph. You can probably just Google it if you want. But the x-axis would be time, and the y-axis would be water flow. So the hydrograph would look different for different watersheds. Okay? And that's important because it'll tell you at what point how much water is going to reach the end. Now, how would you create such a thing? Well, let's just simplify the problem a little bit and say that the only effect of how quickly the water will flow is the change in direction. In other words, the change. So So how quickly the water flows is related to the slope, basically. So then you could determine with just the slope and the upslope flow length, you could determine how much water was going to be at this point at a certain period of time. So hydrologists use GIS systems to figure that out. Oftentimes it's a little bit more of a complex process because it does involve land cover type as well. Sometimes that gets boiled down into a surface roughness coefficient and a curve number. Curve number representing how much water leaves the cell versus how much stays in the cell. We're going to get into this process a little bit in the lab, so we'll have a chance to explore that in greater detail. So the way that GIS systems currently implement hydrologic modeling is that they model the way that water flows off the surface by deriving a local drain direction for every single cell. Okay? It's very, very similar to slope. It's slightly different though. Okay? Instead of inspecting all the neighborhood cells using a window and deriving a slope value for the center cell, we're only interested in examining the neighboring cells and determining which way water flows out of that cell. And the direction that water flows out of the cell is modeled as the direction where the greatest slope is occurring. So here with the target cell, which direction is the greatest slope? We've got a 10 to, it's the greatest downward slope, by the way. So 10 to 12, that's not even downward. 10 to 13, that's not even downward. You see, water doesn't flow uphill. Talk about that, right? So now we'll look at these cells and say, well, 10 to 10, water doesn't flow. Well, it does come sometimes if it accumulates. Okay? But there's two candidates here. The water could flow this direction or the water could flow this direction. So the GIS system will model water as flowing in this direction. Basically, if this is a raster that's oriented north at the top, that would be in a southeast direction. Southwest direction. Because it's the greatest directional change. So that would be defined as 10 minus 8, 10 minus 10, 10 minus 10, 10 minus 9. Which one of those has the greatest difference? And 10, what's that? 10 minus 8, yeah. And actually, the GIS system does account for the difference. So it looks at the rise over the run. So technically, it's not just as simple as 10 minus 8. So it's 10 minus 8, which is 2. And then the run in that case, though, is the square root of 2 times the cell size, rather than just the cell size. All right. But you don't have to actually calculate that yourself. For 1 year, I tried to do that. So you could implement this as a really huge neighborhood operation where you had 8 different neighborhood operations, and you just had negative ones and ones. You had negative 1 here and a 1 here, negative 1 here and a 1 here, and negative 1 here, and so you'd have a pair of values. And so what you'd be doing with a negative 1 and a 1 is you're looking at the difference between these, the difference between these, the difference between these, and so on. And then you multiply that by, in these cases you divide that by the cell size. In these cases you divide it by the cell size. So you could build a model to actually do what ArcGIS is doing. So that's one of the points, though, for the class, is that ArcGIS is simply implementing image processing techniques in order to model these processes. Okay. All right, so I talked about that. So there's several algorithms for calculating the local drain direction. What I talked to you is the most commonly widely adopted algorithm. This is the one that's discussed a little bit in the paper. The paper also talks a little bit about the ability of the system that it uses to adapt to other algorithms. Okay. So, and we'll discuss that in a second. But the D here stands for deterministic. So, yeah, like I said before, it's a simple cell size times the diagonal cells. So these are the actual values. All right, so what happens is that the output of determining which direction the cells will, which direction the water will flow out of the cell is what's called a flow direction raster. And the flow direction raster is coded like this. This is discussed in the reading in the paper that I had you all read. So in the middle here, one of these values is stored. A 1, a 2, a 4, a 6, 8, 32, 64, or 128. One of those values is stored in the focus cell. So if the water is flowing directly to the east, a 1 is stored. If the water is flowing directly to the west, the value that's stored is a 16. So why didn't they just put 1, 2, 3, 4, 5, 6, 7, 8, or some other scheme? Yeah, well, exactly. For some reason, base 2 is better. We'll explain why. You're right that it's just doubling. 1, 2, 4, 8, 16, 32 are just doubles of each other. So for this particular arrangement of drop values, it would be flowing south. So it would have a value of 4. That's why a 4 gets stored there. A 4 means that it's flowing south. Sorry about the colors. Those are horrible. So, yeah, I asked why would we use that schematic? Well, the authors of this paper explain that it gives you the ability to come up with unique values in cases where the drops are the same. So even if there are in two directions where the slope is the same, what you can do is code the addition of both of those two values. So if the drops were the same in the east and the west direction, you could code that as 17, 16 plus 1. So you could put a 17 here. And if the drop was north or south, north and south, you could code them as 68. Or if it was the same in three directions, this direction, and this direction, it would be 64 plus 16 plus 1. Right, the direction could never be confused. So the only way to get the maximum number is that all the directions are the same. In practice, that doesn't happen very often because most often elevation data sets are, at least nowadays, like I'm sure that when this happened, elevation data sets were not always contiguous, with decimal points. But in practice, this rarely happens. But if you did, particularly with data sets, like LiDAR data sets that are very precise, that have a couple of significant digits, then you're not going to get this as often. You're especially, even with an integer data set, it's going to be really hard to get diagonal flows that are exactly the same as straight on flows because the run is different. So one's going to be slightly higher than the other. So that describes this figure from the paper describes this this process. So temporally encoded as 1 plus 2 plus 4 equals 7. Now there is a little bit more complexity to the issue because it's then resolved using the current implemented algorithm. There is a fixed. It comes up with a single way that the water flows for every single cell, but you don't have to do that. You can come up with your own algorithm for how water flows out of the cells.
But for this particular implementation, it's implemented in ArcGIS that's described in this paper. There is a more complex algorithm that then makes a determination which way it's going to flow. This is the output of a flow direction. Whoops, messed up there. This is the output of a flow direction data set. So for every cell, we get a value that represents which way the water is flowing out. So the things that say east here, what I've really done is just coded those values that were 1, and I'm showing them as east. So this was 1, this is 2, and this is 4, 6, 8, 10, sorry, 8, I don't know, not 6. 1, 2, 4, 8, 16, 32, and so on. I was just going by twos, counting by twos. 2, 4, 6, 8. All right. Hydrologic modeling. So, it's not quite as straightforward as I talked about. There are some issues that occur. One of the issues that can occur is that your data set contains errors. Most DEMs have some problems with them. We discussed some of those last week. If you have a freeway overpass or whatnot. One way to deal with these sort of things, freeway overpasses, by the way, will create these issues called sinks. Sometimes sinks actually exist in nature, right? Like there's somebody actually dug a pond and he put a dam up, and so there actually is a sink. So a sink represents an area where the flow direction is always getting back on itself, and you reach the bottom eventually. Okay? It doesn't have an outlet. So some sinks are erroneously created, okay? And some sinks can be real. But in either case, if you actually want to make a map where everything is inside of a watershed, you need to remove sinks prior to performing the hydrologic modeling. So, what does it do? Well, when you fill sinks, when you remove the sinks, what you're doing is you're artificially saying, well, you're just not artificially, you're assuming that eventually all the sinks would fill up with water and then they would pour out at their lowest point. All right, so this is one of the things that you're going to do in the lab. This is the first step. Often the first step in hydrologic modeling is to do what we call fill sinks. So here is an example of a sink. If this was a digital elevation model, water could not flow out of this area because it would actually be flowing in. Water flow direction for this cell would be this way. The flow direction, though, for this cell is also this way. The flow direction for that cell is this direction. So all of these cells flow into this cell. Therefore, that's a sink. So if I want to actually create a model where this is the outflow area, I would have to fill the sinks, and it would adjust the values here accordingly so that the water could flow out of that area. Here's a two-dimensional rendering using a digital elevation model with cells. So this would be a sink. This is a peak. Both of them could be a problem. Both of them could create effective sinks. However, the way it's implemented in ArcGIS is only to fill sinks. So if you want to actually get rid of peaks, you need to identify those first and remove them manually. Speaking of removing things manually, this process is often a manual process, what we call drainage enforcement. Drainage enforcement can be automated a little bit by using existing hydrographic features. So in other words, if you already had lines that represented streams or other drainage network features, you could use those to force
any sinks that occur along those boundaries as you could smooth those areas back out. Okay? You could take the DEM in those areas and adjust them to match the the water flow. Okay? Or you could do it manually. Okay? You'll notice that the effect of sinks is more drastic and causes more errors in small drainage basins and in drainage basins that are flat, more flat to begin with. That might seem counterintuitive, but if they're flat, the error associated with the elevation is within the elevation variations are within the error associated with it. And so if you get a lot of random noise, who knows where the water is really going? So sometimes it's not appropriate to use hydrologic modeling like this in a really flat area, particularly if you know that the average variation between the error is really is within the variation of the data set itself. Okay, so the operation is sometimes called fill sinks, sometimes it's just called sinks. It is an iterative process. Basically, it calculates flow direction, finds out that they're sinks, raises them up, calculates it again, because sometimes filling one sink results in creating another sink. And so it runs a few times until it converges on a solution and creates a data set that it can flow out. This is a screen capture, or what do you call it? This is one of the tables in the article that I assigned for reading. I'm just trying to make it a little bit bigger. This is the procedure that you would do in order to model flow. So the first thing that you do is execute the fill sinks routine that basically iteratively calculates flow direction and fills all the sinks that are occurring. Okay. Sometimes you can just run a routine that identifies sinks, and you could say, well, that's a real sink and I want to leave it in there. In which case, you'd realize that those watersheds will be pretty small. Okay. Then you just run the compute flow direction tool, and at that point, once you have flow direction, you can create other derivatives like upslope area, flow accumulation, and then you can mark a point, and the flow direction raster can be used to determine a watershed. So that's another derivative that you can create. So flow accumulation is another thing that I just mentioned. Flow accumulation is a way that you can model where streams are going to occur. So flow direction tells us about which direction water will flow out of a cell, and it basically builds a network for us. We can trace either forward or backward through that network based on the flow direction values. And so that's a pretty easy routine for the computer to automate. And so for every cell, it can figure out how many other cells flow into that cell. So the flow accumulation raster is, when it's produced, every cell is filled with a value that represents how many other cells flow into that raster cell. Okay. So it's basically the accumulated flow for that particular cell. So what can you do with this? Well, one of the things is that you can take this and you can threshold it by accumulation. You can model where streams probably exist as cells with high accumulation. So a flow accumulation raster looks like this by default. lots of values that are nearly identical, and then everywhere where flow has accumulated, you get higher and higher values. So as we go down this modeled stream channel, we get higher and higher values because they're building on each other. You can also use it to calculate flow length. So for every cell, the flow length raster is the distance that it takes, the distance that that you can travel back up to the top of the watershed. All right, so we've talked about a number of different derivatives, but here's a flow chart that that you would utilize to run these different tools. These are executed as tools in ArcGIS. So you start off with the DEM. And with the DEM, you can calculate flow direction. You don't even need a pour point yet to calculate flow direction. And then flow direction can be used to derive sinks. Oftentimes, this is just a single tool called identify sinks or fill sinks in ArcGIS, and that's the way it is in ArcGIS. It's kind of an iterative process. So if there are sinks, fill them up. If there aren't sinks, you can continue. Usually there's at least some sinks because they're just created through errors in your data, small errors in your data. Okay. Once you have a flow direction data set that's sink-free, you can create watersheds by defining a pour point. You can create streams from flow accumulation, and you can create the flow path length for every cell by using flow length. All right, there are a few other tools in ArcGIS and other GIS software packages. One of them is called Snap Pour Point. Sometimes, in my situation where I talked about Venice, remember? If I went down to Venice and just stood on somebody's lot, it's very possible that I would get a really, really small watershed, okay, that wouldn't include half of the United States. So sometimes when you're dealing with a digital elevation data set, you drop a pour point on an elevation data set, you think you're going to get a really big watershed, but sometimes you get a tiny, tiny watershed. What Snap Pour Point does is it allows you to specify a pour point, but then also specify a threshold and say, okay, it looks for the greatest flow accumulation in that neighborhood and assumes that you meant that pour point. So you can use it to define the actual watershed for the surrounding area rather than a maybe too specific location. So that's what Snap Pour Point does. So we'll demonstrate these. You can use the watershed tool to delineate a watershed. You can use the basin tool to delineate basins, which are areas of a watershed that share similar flow lengths. All right, so this is kind of a review. All right, so we're gonna. One of the first things that the lab asks you to do today is to actually work this out by hand. To not do it in ArcGIS, but to do it by hand first. So here is a elevation data set, and here is the resulting flow direction grid. And the lab, I'm actually going to ask you to use those numbers that were described in the article, 1, 2, 4, 8, and so on. There's a better diagram here. I told you before that the flow direction grid does, one of the things that it's doing is creating this implied network. For every cell has a direction, and so there's only one way to work yourself through that network, either forward or backward. Well, I guess backward there are sometimes multiple ways to go upstream, but downstream only one direction. So flow accumulation tells us how many cells are upstream. See how this value is 20? It's 20 because it's the addition of all of the cells in this direction. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. I must have missed some, but I'm getting close to 20. So the 20 cells here, all these cells flow into that cell. So this is what it looks like in the output raster. I could then decide anything that has a flow accumulation of greater than 6 is a stream. That's probably a pretty low threshold, but in my silly example, my small example, I could do 6 as the example. Anything that's 0 is a watershed boundary. In other words, no water flows into that cell. Water only flows out of that cell. That's what that implies. So you could you could actually reclassify all the zeros, and you would know what? What do the zeros represent? What did we call that on one of the other previous slides? Or just what do you call that in general? Yeah, the boundary. What's another word for a watershed boundary? Yes, a divide. Yeah, so those are the divides. Good. Awesome, you guys are getting that. Okay, flow accumulation. This is a really old program called ArcView. I should totally update this. I already showed ArcView. Okay. So now we're gonna actually implement that. Once you create a watershed, you can use them for all sorts of things. You can use them to define. You can create a watershed anywhere, and what's useful is that you can use that to determine the amount of water that's going to reach a certain culvert, a bridge, so you can decide if that bridge is big enough to fit the water through it, or the culvert is big enough to fit water through it. That's some of the ways that this data is implemented. Okay. Now in ArcGIS, you can implement a pour point as an entire thematic layer, or they can be created by selecting a pour point on the screen. It depends on what data set, what tool you're using to implement it. So we'll show that here in a second. So you can let ArcGIS Spatial Analyst automatically generate watersheds for an entire area. So here might be the pour point for this area here. You can also say, okay, I want to just create catchments. And I want my catchments to be a minimum of 5,000 cells. So what it does is it just defines watersheds that have a minimum 5,000 cells in them and shows them to you. The United States government actually creates these sorts of catchments. They call them hydrologic units, something. They're called HUCs, H-U-C. They've created these for the United States. You can download the HUC data sets where they've generated these things. Okay, I'm going to stop there. And we're going to come back to the slide here, this last slide here as part of the lab. Okay. I've only been talking for about an hour now, so I don't know if anybody wants to take a break or just go into the lab. What do you guys think? I'm willing to take a vote today. Okay. All right, we'll take a break. I actually am going to go to the bathroom too. So I will come back. It'll be good to break up the video and make sure it all records anyway.